Good morning or afternoon to everybody. I'm very pleased to be hosting this week's seminar speaker, Dr. Jim Conca, whom I've never met in person, but have corresponded with for a number of years now, mostly dealing with environmental radioactivity issues. This started initially with our mutual interest in the Fukushima event in Japan, which you'll recall occurred in 2011. But we've expanded our discussions, our email discussions over the years to other issues as well. I've been trying to get Jim here for some time now to give a presentation on his writings and thoughts on environmental radioactivity and environmental issues dealing with energy production in general. He writes, contributes weekly essays, I think it's weekly, to Forbes magazine. And they are very entertaining and provocative essays. I end up learning something from virtually everyone.
Thank you.
And Jim, let's see, his background is as I believe a biochemistry major at Brown University for his undergraduate, and then did a master's and PhD at Caltech in geochemistry. Geochemistry, is that right? Or
yes.
Something along those lines.
All of it was planetary science related.
Oh, I beg your pardon. Okay. Yeah. Has done some work in the Antarctic, has a long-time affiliation with Los Alamos Lab in New Mexico, started his own sort of DOE spin-off firm in near the Hanford Reservation in eastern Washington State, called UFA Ventures, I believe, something like that.
Yep, it's unsaturated flow apparatus.
Okay, thank you. And so today's talk is going to be on environmental radioactivity, to what extent should we worry about it, and how it may influence our thinking on disposal of nuclear waste somewhere on this planet. So without any further comments from me, I'm pleased to give you Jim Conca. Jim?
Great, thank you so much. This is great. I'm going to take over the screen now, correct?
Yes.
Might as well just kind of jump into it. In fact, what I started out in all of this was actually after Caltech was at JPL, and the biochemistry was looking at origin of life on Earth and exobiology on other planets. So whenever you hear about Mars, that was what I was doing. Very interesting. It gives you a weird perspective on things as well, a global perspective. So it's perfect for nuclear to step. Well, actually, I was coordinator of shuttle activities over the poles when the Challenger blew up in 1986, and that kind of, all of us youngins lost our positions there. And many of us went into nuclear, which is kind of weird. But it actually works because it's another weird subject that requires out-of-the-box thinking. So it kind of fit well. So I'm going to talk about radiation and the value of a human life. Pretty much, low radiation limits. People talk about radiation, they talk about what's dangerous and not dangerous, and almost everything you hear is worthless. It has nothing to do with reality. They're just I hate to say that, it's regulatory issues that always get talked about. So whenever something happens and they talk about how dangerous something is, they're just talking about a regulatory administrative issue. They're never talking about science or epidemiology or anything like that. And so I kind of want to get back, because these, when you get off into non-reality where administration takes over science, which we can see that right now in this country, bad things happen, stupid things happen, and it mainly costs a lot more than it should. So what has inappropriately low radiation limits done to our nuclear program? So that's what I kind of want to talk about. So the problem as it stands right now, radiation risks to humans and the environment are assumed to exist as a result of any exposure to radiation, no matter how small or how low the level of exposure is. And that's something called the linear no threshold dose hypothesis, which I'm not sure any of you have heard of or talked or thought about. So, and we'll get into that. Exposure to natural background is, on average, about 300 millirem or 3 millisieverts. Now, I'm going to use all these units. And units are units. Just think of this: 1 sievert is bad. 1 sievert is bad. You need to run if you're getting a sievert. Okay, so 3 millisieverts is not. 3 millisieverts. In fact, okay, you're in Stony Brook, so the background's about 300 millisieverts, right? About 300 millirem. I'm sorry, about 3 millisieverts, 300 millirem. And that's mainly from things like soil and dirt, a little bit of cosmic rays. If you eat a lot of potato chips, you probably know potato chips are the most radioactive food. You know that? Very interesting. 13,000 picocuries per bag. Wow, what's a picocurie? Okay, well, anyway, so mainly it comes from natural materials, food, cosmic rays, but about 300 millirem per year. So just keep that number in mind. However, the global averages range dramatically from 0.03 millisieverts, or 100th of what you all are experiencing sitting there, to 100th if you're out in the middle of the Atlantic Ocean or the middle of the Pacific Ocean. It's much lower. And then up to over 100 millisieverts, or 10,000 millirem, 10 rem. If you're, in certain parts of the world like Brazil or Iran or the upper Rockies, Rocky Mountains in the United States. So again, it depends on where you are, pretty much how much uranium is in the rock around you, producing radon and other materials, thorium, things like that. So it changes dramatically over the Earth's surface. Now, it is not possible to see statistical evidence of public health risks at exposures less than 10 rem. And oh my God, that's the upper background across the Earth. So background across the Earth has never caused any health issues that we can measure, okay? And since we're looking at billions of people, the statistical power is pretty good. Now, the reason we never see anything is because the other risks are well below the noise level of cancers faced by everyone. I mean, people get cancer. About 35% of the population will get cancer, period. None of that, so much less than 1%, we can't even measure it, will get it because of radiation. So it's very, very difficult to get cancer from radiation because it's hard to get that large a dose. So as an example of this problem is that regulations require nuclear waste disposal systems to meet a release criteria, meaning they cannot release more than 0.04 millisieverts per year to down gradient drinking water supplies. Now, if you look above in the second paragraph, that's as low as background is ever on Earth. Okay, it's about 100 times less than what you all are getting right now. So the idea that we're going to spend at this point about $300 billion to get it down to 100th of what background is, you really might question that, whether that's a good use of money, and we'll talk about why. So what are the costs of regulating these doses to such low levels? And a better question might be, how much do we consider the value of a human life to be? This is an ethical issue, not necessarily a scientific issue. This is definitely an ethical issue. So the United States government considers the value of a human life to be $7 million. Not sure if you knew that. I kind of wish it was, I'd give up my life to get Judith, $7 million. That's kind of funny. I mean, EPA uses that to assess the costs of environmental contamination that will kill you, okay? And that's how they kind of model the cost to society and the cost to human life. So now, a better measure is probably the healthcare industry, which deals with death all the time. The average healthcare paid out over a life in America is about $316,000. Now, some people spend millions staying alive. Some people don't spend anything. But it averages about $316,000 paid out to the average person that has healthcare in this country. Now, of course, lawyers know this better than anyone else. The average value of wrongful death suits in America is about $129,000. Now, if you're a celebrity, you're going to get millions. If you're, again, a homeless person, you're not going to get anything. But the average is $129,000 paid out in wrongful death suits in America. Now, this is kind of disgusting. The death benefit to families of deceased soldiers is a whopping $12,000. Now, if you're certain situations in the battlefield, you can get more, but this is the average death benefit to the families of soldiers. Notice how much smaller it is than everything else. Now, if you're a healthy young person, like many people watching right now, if we chop you up and sell you on the black market, you're going to bring in about $45 million. That's pretty good. Now, if you're a Department of Energy trying to meet these low levels, we are going to spend $2.5 billion per theoretical, not real, but theoretical human life saved in the next 1,000 years. 2.5 billion. There's a little kitty, hey. That's rather astounding. So we don't spend that much money saving a real life now, but we are spending that to save a theoretical human life in the year 4000. What's even worse is that if we actually took just that one life saved by the Department of Energy, 2.5 billion, we could immunize almost the entire continent of Africa and save about 25 million lives, because it only takes $100 per person to immunize against the 3 biggest scourges in developing countries. So keep those in mind when we're talking about the amount of money we're spending to save theoretical human life from low levels of radiation. Now, so I mentioned LNT, so the linear no threshold dose hypothesis. What it says is that no matter what the level of radiation, right down to 0, it's simply a straight line relative to the effects, whether it's cancer, whether it's acute radiation sickness or death or whatever. From high doses to low doses, it just is a straight line through 0. Now, they picked that, of course, because it's easy. I mean, no one likes to solve quadratic equations or even differential equations if you can help it. And this is mx plus b without even a b. Okay, so this is about as easy a mathematical situation as you can get. Now, here's Earth background I mentioned. And it turns out there is a threshold. It actually is about the top, near the top of Earth background. And that makes sense because the eukaryotic cell, okay, we're all made of eukaryotic cells, which are, not prokaryotes, so we have a nucleus and all that. The eukaryotic cell emerged about 2.3 billion years ago when oxygen first began to enter the atmosphere. Now that's critical because oxygen is about 1,000 times more effective at causing damage to DNA and cells than radiation. Okay, so radiation is a pretty weak mutagen, cytogen, and carcinogen, whereas oxygen is very, very powerful. So the repair mechanisms to oxidative damage, which is what radiation does to your cells if it gets high enough, is very, very good in eukaryotic cells. So our cells are really good at repairing DNA damage up to about 10 rem or 0.1 sieverts. So, I'm sorry, 0.1 sieverts. And that makes sense. I mean, if you evolved in fact, 2.3 billion years ago, the background radiation levels on Earth were about 10 times what they are now. So of course, if you're going to evolve under that condition, you're going to be pretty good at repairing what you need to repair. Now, the health risks from doses less than 10 rem cannot be significantly distinguished from zero. So it's not statistically different than zero. And I know scientists hate to say zero, hate to say never, but it is. It's zero. There's no effects from less than 10 rem that we have ever been able to see. And we have been looking really, really hard for the last 75 years. So you have this idea of LNT, right? Just a straight line through zero. Now, if you go to certain areas, Brazil, areas down here, especially Ramsar, Iran, the background radiation in Ramsar is 10 rem. Okay, so that's the background, and they don't have any extra cancers or more cancers. In fact, if you take their stem cells and you subject them to a challenge dose, a pretty high dose, 1.5 gray, which is about the same as 1.5 sieverts, they do better. Okay, so they're better at dealing with radiation because, again, they live in this high background radiation area. But again, there's lots of areas in the Earth on Earth that have fairly large background doses, and we don't see any change in cancer rates in those areas. So what are some of the costs associated with these low limits? Let me go back here. Right now, this is Earth background, and the regulatory limit of 4 millirem per year that DOE has to meet, and that everyone has to meet, is down here. So again, this is the background, and we have to get these systems, we have to engineer them so well that they do not contribute more than 4 millirem per year to any nearby water features. So, so these limits are so far down in the noise as to be meaningless from a public health standpoint. I mean, you're not, if you're living in a 300 or 400 millirem background per year, the idea that you're going to get an extra 4 or not, or an extra 10 or not, really doesn't have any meaning. It's not going to cause any difference. And that's because, again, the noise is the background. And noise is very important here. I mean, think of it from a measurement standpoint. I mean, we can measure radiation really well. But if you're in the background of 300 or 400 millirem per year, and you're trying to deal with 3 to 4, 100 times less, there's just the noise is going to just wipe out any effects. And then the noise of everyday risks. I mean, the risk of driving a car, things like that. Now, we can get into risks later, but risk is a weird thing, and the public doesn't really know how to deal with it. They like risks they can control. They think they can control. So when you talk about smoking cigarettes, which is a huge risk, they say, well, yeah, that's okay, but I'm choosing to do that. Or driving a car, huge risk, but I'm choosing to do that. And then you talk about radiation, and they have no idea because they're not in control. And so they're much more afraid of radiation that has no risk than they are of things that have huge risks, because they think that they're in control of those risks, which is kind of delusional. So LNT, this linear no threshold dose hypothesis, demands, now this is, no one ever talks about this, demands that there is an observable effect as a function of dose. It's not like, so here's, okay, let me just get this. This is the mortality rate of Americans on average as a function of background dose. Now, as you can see, there really isn't any relationship here. I mean, it's kind of funny because the higher the doses in America, like this is Colorado, New Mexico, and other Western states that are high elevation and they have a lot of uranium in the rocks around them, they have lower mortality rates from cancer. So again, that's weird because LNT says there has to be a relationship. So LNT would look like this. It does not look like this. So right there, I mean, that's all you need to know in order to say, well, LNT is not correct at very low doses. It's great at high doses, but it's not very good at low doses. So we look at high doses. This is the atomic bomb survivors cohort. This is in 1994, changes yearly, of course, as people die. But here we have a fairly good linear relationship at high dose. And then you get down to about 10 rem and it just flattens out. And here's the control group. So this is not subject to any radiation from either weapon. And what we're talking about here is this is linear, but there's a threshold. So it's not the linear non-threshold, it's the linear threshold dose hypothesis. Now, if you look at more recently, 2012, same thing. Again, it's kind of linear, although it kind of bows a little here, and then it gets to background. So again, this is background in terms of cancer rates and in terms of background radiation. And again, here's another one from 2009. Again, the atomic bomb survivors. This is the best group of people we have to deal with the health effects of radiation, because there were many of them, more so than Chernobyl. And so again, at higher doses, okay, this time actually over 100 milligray, which is the same as millisievert if you're gamma rays. So again, it's linear, then it gets down to about 10 rem, and it flattens out. And in all of these atomic bomb survivors, there were 812 excess cancers for these 1,600 people. So it's not like everyone who got exposed at Hiroshima and Nagasaki died from cancer, not at all. I mean, it was a significant but relatively small number. So what are some of the costs associated with these? One, the commercial nuclear industry, they gripe all the time. I mean, I'm glad the nuclear industry is so safe, but they gripe all the time that this increases their cost and increases the fear of nuclear power in the public, which it does. People are just irrationally afraid of nuclear energy, which is funny because it's the safest energy source there is, including wind and solar, which we'll look at those numbers. Environmental concerns, this fear of radiation prevents nuclear power from addressing climate change. We shouldn't be shutting down Indian Point. I mean, that is insane. But we are, and it's going to be replaced with natural gas. Now, you may not care about climate change. A lot of people don't. So, you know, it's no biggie. But if you do, like every leading climate scientist from James, oh dear, can't remember his name now. The climate guru, yeah, on down. They say we're not going to do this without nuclear power, and we won't. We will not address climate change at all if we don't have significant nuclear power, or hydropower, or wind, or solar. I mean, you need them all. We don't have the luxury of not using a non-fossil fuel if you want to get rid of fossil fuels. Nuclear waste, it increases the cost, again, of repositories that are very easy and very safe to do, but now we have to get kind of ridiculous in preventing emissions that are 100 times less than background. So you want to put them at the best geographic and geological locations, but the fear of radiation makes the people there not want it. And you might say, well, I don't want nuclear waste in my backyard. Okay, that's fine. But you only need one repository and we need to put it someplace, or it just stays right where it is, which is a whole other talk, which I'd love to come back and do. Medicine, this is important. Radiation phobia prevents certain medical diagnostics and treatments involving radiation. People, and we know this, you know, radiation oncologists I work with all the time, people die instead of get a treatment. Okay, now that's insane. And it's especially pertinent right now because COVID-19 can be treated with low levels of radiation. It doesn't kill the organism itself. It doesn't kill the coronavirus. What it does is reverse the cytokine storm that is the cause of 90% of the deaths from COVID is an immune response called a cytokine storm. And low levels of radiation, we do this all the time with cancer, even at 100 times less than the doses we use for cancer, will reverse the cytokine storm and the person recovers fairly quickly, within about 24 hours. And we're not doing this. And that is unethical. Again, this isn't necessarily a scientific issue. This is an ethical issue. 180,000 of the 212,000 people that have died should not have died. They just needed to spend 15 minutes in radiology. Now that's it sounds radical, but it's not. We've been doing this for a long time. We know viral pneumonia responds very well to low levels of radiation. Low levels, not high, low levels. And then emergency preparedness. I'm going to actually give a training to a Coast Guard group that has a nuclear power plant on shore, close to them, to where they patrol, and they're all freaked out about a Fukushima-like event, and so it might cause them to not respond correctly because of this. So again, we'll go over Fukushima, Chernobyl, and a dirty bomb attack kind of thing. But no one died from radiation at Fukushima. No one ever will. There was not enough release. There was not enough dose to anyone. But the extreme hasty evacuation, forced evacuation, killed about 1,600 people, mainly because of medical issues. And that didn't need to happen. And the same thing with Chernobyl. More people died from fear of radiation than from radiation from Chernobyl itself. And we'll get into those numbers. So if you're going to actually have any reasonable emergency planning and execution for future disasters, you better understand the actual health effects of radiation. Now, the extreme phobia following a nuclear or radiological event, again, loss of lives and severe injuries associated with frantic evacuations. Now that occurred both at Chernobyl and Fukushima. Increased suicide. This is a horrible thing, but it's very common, especially in Chernobyl. 50,000 people died after Chernobyl from alcoholism, suicide, and psychosomatic disorders related to the fear of radiation. They didn't get any dose worth mentioning, but the fear that they did killed 15,000. There was also about 100,000 unnecessary abortions performed in the 6 months following Chernobyl from people that never got any dose from it, which is actually very strange and horrible in its own way. And then the extreme cost of cleanup relative to the actual risk. Again, if you have to clean up to 4 millirem a year and the background is 400, it's going to cost you an awful lot. And that money is better spent on other health issues than that. So Fukushima, I don't know if many of you understand what actually happened, but there was no nuclear explosion. I mean, you probably know that, right? Unfortunately, the people whose lives had already been destroyed by the tsunami, it's absolutely can be forgiven, did a couple of very foolish things in the week following. They vented the hydrogen inside the building instead of to the atmosphere, which again, they were worried about tritium. Now tritium is just nothing. I mean, there's no health effects from tritium. So instead of putting the hydrogen gas to the atmosphere, which would have caused no problems, they vented it to inside the building. And of course it blew up. And that's the explosions came from hydrogen, not a nuclear explosion. Now, again, the prefectures around Fukushima, especially Ayatati, were forced to evacuate quickly. They didn't need to evacuate quickly, but they were forced to, and it killed about 1,600 deaths, mainly elderly and disabled, who should not have been moved. Now, most adults could have returned after 2 months after iodine-131 decayed away to nothing. Its half-life is 8 days. I assume you know what a half-life is, so 8 days, half of it's left, blah, 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 blah. The rule of thumb is 7 or 8 half-lives to background. So after 2 months, the worst radioisotope that was released, iodine-131, was gone. According to the WHO, there's no acute radiation injuries or deaths among workers or the public from any exposure from radiation from Fukushima. There just was not enough released, and it did not build up in any amount except right around the reactors. And even there, no one got enough of a dose. The lifetime radiation for cancers are much smaller than the lifetime baseline of cancer risk. So again, when we say out of 100,000 population, 35,000 will die of cancer. 35,000 plus or minus 4,000. So what that means is that year to year, if 36,000 die or 34,000 die, it's the same as 35 because it's 35,000 plus or minus 4,000. So you will never see small numbers, even if they existed, resulting from this because the error in these large numbers is so high. I mean, or the noise from ordinary cancer risks totally overwhelm anything that can occur from these levels of radiation. Now, for about 160 workers who received whole body doses effectively of over 10 rem or 100 millisieverts, even they won't get any detectable statistical number of cancer risks because the risk of other cancers is so high. Some of the costs associated with emergency preparedness and execution. So over 50% of residents have finally returned to Fukushima, mostly older citizens. But the government estimates the cost at over 200 billion for that evacuation. At an average of 39,000 per capita GDP, the revenue losses since 2011 exceeded $40 billion for that number of people. There's been 12 billion in compensation paid for displaced residents. And then again, they shut down all of the nuclear power plants. Almost all of them were not at risk. I mean, there's only 11 that could possibly have a tsunami associated with them. And I should back up a little bit and say, you know, Fukushima Daiichi, we had been telling them for about 10 years that their seawall was crap, that their backup generation was totally inadequate. And they ignored us. And that's too bad because this was totally unnecessary. But again, they had 55 nuclear power plants running at that time. They shut them all down. They've only started up a few of them. And most of them were not at any risk at all. But they had to increase fossil fuel as a result of that by about 20%. Energy prices increased about 20%. And as you know, using coal and oil have their own associated deaths, risks of death, mainly from particulates. And so the estimates are we're going to have about 15,000 additional premature deaths because of the increase in fossil fuel. There was no death from radiation. So again, you have to weigh this. This is all relative. Risks are best looked at relative to other risks. And so this was not a very good choice. Now, what's even weirder is that the government, Japan's government, lowered the radiation limits on food. Now, when you have an incident like this, you usually raise the limits because you may have a short temporary time period where levels are a little higher. But there was no increased levels in anything. But the government lowered the limits, thinking that it would appear as being proactive. So they dropped them by almost an order of magnitude. Now, that's kind of bizarre. So foodstuffs, and the units here is becquerel per kilogram. Becquerel is a disintegration. So when a radioactive nucleus emits radiation, it disintegrates. So we talk about disintegration. So disintegration per kilogram of food. So Japan dropped the limit to 100 becquerel per kilogram for food. Now there are mushrooms that grow everywhere in the world that are twice this. And so suddenly all the mushroom farmers in Japan couldn't sell their mushrooms because they were over 100 becquerel per kilogram. And as you know, potato chips are the most radioactive food. So they didn't realize that they had pretty much outlawed potato chips, but they didn't realize that and they didn't do anything. So potato chips here they lowered their radioactive food limit, radioactivity in foods to below where potato chips are safe. Very strange. Because of this is a very bad move. And again, just because of fear of radiation, they destroyed much of the farming and fishing industry in northern Japan, mostly in areas that were unaffected by any radiation. Ironically, something we call the Chernobyl effect, the Fukushima disaster proved to make the fisheries off the coast basically protected marine areas, and fishing stocks have tripled in these waters because they haven't been fishing them. Just like around Chernobyl, bears and wolves and wild animals have blossomed because there's no humans. Because of course, we know that the biggest contaminant on Earth is human beings. That's supposed to get a laugh. Okay, so what are the costs to the nuclear industry for these limits that are associated with the linear no threshold dose hypothesis? Nuclear power plants spend about $20 million a year in rad protection. That's fine. Waste handling and emergency prep, in large part to address the fear based on LNT. So about $1 billion a year for the industry. Premature closings and plant shutdowns, that's what is worrying me and should worry you if you care at all about the climate. We are going to be closing another 10, probably 10 nuclear power plants by 2025. There's no reason. They were all of them were rated safe and given another 20-year license extension by the Nuclear Regulatory Commission. So there's no problem. It's simply just short-term profits, fear, and politics. So that's bad. And although we're not going to talk about the Green New Deal or anything, subsidies for non-fossil fuel energy sources like wind and solar average about 2.5 cents a kilowatt hour. The nuclear industry would like 1 cent a kilowatt hour, but that's not actually happening very much. So the idea that you care about the climate, you want to save the planet, but a penny a kilowatt hour is too much to pay, just kind of appears illogical. So as a result of these premature closings, actually there's 25 of them, 5 trillion kilowatt hours of low carbon power worth about 800 billion will be lost. It will be replaced by natural gas. Every time we close a nuclear power plant, it's replaced by natural gas, not wind, not hydro, natural gas. 600,000 man years of direct labor will be lost, 2 million man years of indirect jobs, over 6 billion in local taxes, and there will be 15,000 tons of orphaned spent nuclear fuel. And this is kind of strange too, because if you have, I mean, there's not much spent fuel anyway. It takes so little fuel to create nuclear power. But if your nuclear power plant is running and producing power and producing money and paying into the nuclear fund, the nuclear waste fund, then you can have this spent fuel stored on site until it goes to a repository. But if you foolishly close the plant early, 20 or 40 years early, then you're going to have all this spent nuclear fuel orphaned on site, and you don't have a working power plant, so you're not generating any fund to take care of that. So again, you're just orphaned, you're orphaning a bunch of spent nuclear fuel that has its own issues associated with it. The effect on nuclear waste disposal has pretty much been to completely stop our nuclear waste disposal program because of fear. I mean, we're not disposing of nuclear waste, high-level waste or spent nuclear fuel. We're disposing of transuranic waste, which we can get into in a little bit. But essentially, this total fear of low levels of radiation means we've made some very bad non-science-based decisions. And again, when science is thrown out in favor of non-science issues, we usually pay for it one way or another. So right now, LNT gave us glass over grout. Now, we have high-level waste, which by definition is weapons waste, and it's the gunky peanut butter-like consistency in the tanks up here at Hanford, and there's other waste around the country. I'm not sure, I don't think New York has any defense waste like that. They have defense glass that they've already turned into glass. But generally, the waste form you put your high-level waste into is important from a standpoint of cost and a standpoint of safety. So when you have high-level waste and you turn it into a material, either you vitrify it, turn it into glass, or grout it, turn it into cement, you cannot have any free liquid. That's why you do this. You can't get it on the road. You can't meet Department of Transportation requirements if you have even 1% of free liquid. So you're trying to make it dry so it cannot leak. Now, grout, turns out, there are formulations that are better in terms of performance, leachability, things like that, even strength, than glass. But we chose glass over grout because of fear. So the Hanford vitrification program that you probably have heard of, not including repository costs like Yucca Mountain, are going to exceed $90 billion. They were only supposed to be 20, but they're up to 90 now. If you just grouted this, it would be 30 billion. So again, making bad decisions based on fear cost us a lot more. And there's no difference in the risks of making high-level waste grout or glass or minerals or of any sort. There's no benefit gained for either one of them, so you simply want to make it into a dry material. It's also made it impossible to site a repository. So Yucca Mountain, the fear of radiation has made Nevada absolutely reject Yucca Mountain in so many lawsuits that you can't even count them. And it's also prevented us from reclassifying waste, which I'll talk about. And then it's given us ridiculous requirements at places like Yucca Mountain, where we have over 7 engineered barriers, like titanium drip shields, that again have increased the cost now to over 200 billion. It was supposed to be 30, but now it's over 200 billion. So again, it may not seem like much. The idea of, well, I'm really afraid of low levels of radiation, so we really have to make it super safe. And that sounds great. It sounds conservative. You might say, well, we're just being conservative. But when the costs start multiplying with no benefit, then it really is not conservative. It's simply foolish, and you're wasting money we desperately need in other ways. So, nuclear waste, Hanford site. That's where I am right now. It's on the banks of the Columbia River. It's a weapons complex, and it's a very complicated subsurface geology before things get out to the river. Not sure if you know much about nuclear waste. There are 4 categories in the United States. This is different than Europe. Spent nuclear fuel is the hottest material. High-level waste is the next hottest, transuranic waste, and low-level waste. Now, high-level waste and transuranic waste are by definition weapons waste. Okay, spent nuclear fuel is not high-level waste. High-level waste is only weapons waste. Transuranic waste is only weapons waste. Spent nuclear fuel looks like this. This is a fuel bundle inside a reactor. It is solid. It's metal. Okay, there's no liquid in there. It's not something that can leak easily. In fact, it's very easy to handle and very easy to shield. High-level waste, here's inside of a tank up at Hanford. It's T101, I think. It's this gunky peanut butter-like junk that you kind of associate with The Simpsons. I love The Simpsons. When their green goo starts leaking out of the reactor, that has nothing to do with an actual power reactor. That green goo is more like weapons waste in the tanks. It very kind of, this you have to form into another material because this is gunky peanut butter. You really can't transport this very easily. You must solidify it some way, either grout or vitrification. Now, transuranic waste is a funny thing. No one ever hears about it. It's all the other stuff left over from making weapons that's been contaminated with plutonium and americium, neptunium, things like that, but mainly plutonium. And it can be anything. It can be grout, it can be cement, it can be old PPE, it can be chopped up glove boxes. It can be anything that is contaminated with plutonium above a certain amount. And then low-level waste is pretty much dirt. I mean, most of our low-level waste in this country is dirt, but it's anything that is contaminated and is below a certain level of activity, of radioactivity. We have a lot of that. It does not require deep geologic disposal. The top 3, deep geologic disposal is required for spent nuclear fuel, high-level waste, and transuranics by law. So they have to go into a deep geologic repository, which is great. As a geologist, geochemist, there's great places to put this stuff. Unfortunately, it's not Yucca Mountain, but that's another talk. Now, New York State has all four types of nuclear waste to some degree, but mainly it's spent nuclear fuel in New York State. There's a little bit of weapons waste and low-level waste. So, a short nuclear primer. Uranium-235 splits easily. 238 does not split easily. You mine uranium just like you mine iron. It comes in a rock. Various different types of rock contain uranium at significant amounts. You smelt it, you separate the yellow cake out of it, and then you have to enrich it if you want to do anything with it. Because natural uranium ore is only 0.7% 235. It's almost all 238. And that's not enough to sustain control chain reactions for the most part. Now, the funny thing is that everything that I'm touching, that you're touching, the walls, uranium, everything above helium on Earth was created about 6.3 billion years ago in a supernova explosion next to our condensing solar nebula. So everything heavy was produced during that supernova. It's how you can get neutrons, you can squish neutrons together at large amounts with protons into nuclei with that much pressure and temperature. So 235, 238 were formed, again, 6.3 billion years ago. The half-life of 235 is about 700 million years. The half-life of 238 is about 4 billion. So 238 has only been through 1 and a little bit more half-life. 235 has been through 9 half-lives, so there's not much of it left. That's why this is the case. Now, nuclear fuel for a reactor, depending on the reactor design, you have to enrich to 3 to 5%, whatever. Again, it depends on the reactor design, but let's say about 4%. And still, most of it is 238. Now, if you want a weapon, it has to be all 235 because it has to all fission at the same time. So again, nuclear fuel, weapons. So what happens when a neutron hits a 235 nucleus? It splits into 2 unequal pieces called fission products. You get about 3 neutrons out and a bunch of energy. Okay, 3 for 1, 3 neutrons for 1. That's such a deal. That's why it works. It's why nuclear is so effective. Now, if you're a bomb, then you're all 235, and those 3 neutrons see another 235, and it splits, and now you're at 9, 2781, boom. So in a microsecond, you get about 10 to the 22nd neutrons, 10 to the 22nd fissions. And that has to be the case with a bomb. You want it to all go off at once. Now, the radiation in this process is not important. It's kind of secondary. What's important is the energy, the speed with which these 2 pieces fly apart. So the fission products, the pieces fly apart, and if you have 10 to the 22 flying apart, then you're going to build up a lot of heat and a lot of pressure. And that's the blast. That's what a nuclear bomb is. It's not a radiation device. It's a nuclear bomb. It's a big, big bomb. So when we talk about 13 kilotons that we dropped on Hiroshima, we say 13 kiloton equivalents of TNT. So if you had 13,000 pounds of TNT, you put it all in one place and you could ignite all of it at the same microsecond, you would get the same mushroom cloud, the same blast, the same effect as a nuclear weapon. You could not distinguish them except at the edges, the edge of the blast zone, you'd get a burst of high energy gamma and neutrons. And that's the people, the atomic bomb survivors, were in that zone, that little annulus around the blast, where the blast did not reach them, but this little burst of radiation did. And it was only during that microsecond. There was almost no fallout from Hiroshima and Nagasaki. It was all that one microsecond blast. So that's a bomb. Bomb is a bomb. Now, if you're fuel for a reactor, you're still almost all 238. So you're 96%, uranium-238. And those neutrons generally do not see another 235. They see a 238, which does not split. It captures that neutron and quickly double beta decays to form plutonium-239. You're breeding plutonium from uranium-238. So that when you hear the term breed, that's what they're talking about. You're breeding it. You also breed other actinides as well, but the one you care about is plutonium. Now, if you're a weapons reactor versus a power reactor, this still goes on. You're trying to breed plutonium for a weapon. And the reason you want plutonium versus uranium-235 as a weapon is it takes less plutonium. It's more efficient. In splitting, it produces more power. So you can make your bomb smaller. So if you want to missileize a weapon, you need to make plutonium. And that's why most powers of the world, most nuclear powers in the world, chose to produce plutonium to make weapons. Now, Iran chose uranium at first, and then they started up their Arak reactor, which we shut down as part of the deal, which was a very good deal, by the way. So I'm getting a little off track here. So if you're a weapons reactor, like up at Hanford here, there were 9 of them. You put your fuel in and you only run it for 6 months. Then you take it out and you separate the plutonium. And the reason you don't want to run it longer than 6 months is because you will start breeding in what's called neutron poisons, things like plutonium-240 and 241, 242. So these will not split. They will pretty much scarf up the neutrons, and the thing becomes a dud. So you need to remove the plutonium when it's still all 239. So now in a commercial reactor, you don't care about that. You're not trying to breed weapons, grade plutonium, just trying to produce power. So you leave the fuel in for 6 years. And again, there's so many neutron poisons that you can't make a nuclear weapon out of spent nuclear fuel. We've tried. We made a really crappy device in the 1960s, just pretty much to show it's not worth it. And no one has ever tried because even terrorists know that's a stupid thing to do. So, so in a nuclear reactor, power reactor, you run this, and after about 2 years, you've bred so much plutonium that it is producing more power than the original uranium-238. I'm sorry, 235. And after 5 or 6 years, you've now bred so much, you've now built up the fission products to the point where they start scarfing up all the neutrons and the thing fizzles out. It's not totally spent, it's not done. It's simply, you get too much junk in it. You can reprocess it if you want, recycle if you want, or you can just put it aside and put in new fuel. Since uranium is so cheap and so plentiful, reprocessing really isn't a great thing to do. You don't need to do it. Also, spent fuel can be burned in future fast reactors that we're developing, like Bill Gates. I don't know if you know, Bill Gates has a nuclear company that he started here in Washington State. I visit them all the time, TerraPower. They have a design for a fast reactor, as do a few other people. They can burn this spent fuel and get about 10 times the amount of energy out of it and not increase the waste volume anymore. Okay, now let's get back to weapons because this is what we did up at Hanford. So we took this fuel that had been in the weapons reactor for about 6 months and we dissolve it up and we put it through a series of separations to separate out the plutonium to make weapons and to recover as much uranium as possible. So the definition of high-level waste versus transuranic waste only comes from where in these steps, the material came from. So the first thing you do is you try to separate out uranium and plutonium totally from all the fission products, like cesium and strontium, which are the hottest ones. A lot of fission products are not radioactive at all, and some are so radioactive that their half-lives are in minutes or days or months. So you separate all that out, and that goes into the high-level waste tanks, of which we have about 140 of them here at Hanford. That's all that was. It has nothing to do with the level of radiation or anything else. It's simply coming from these two steps. Now, after that, this polishing steps, basically you're polishing the plutonium, those go into, the waste from those go into the transuranic waste tank. So transuranic, simply, you know, above uranium, so uranium, plutonium, neptunium, the last row in the periodic table, those are the ones that come out of these processes, and they go into the true tanks. Now, most of the waste was high level, but there was a significant number, about 20 of these 500,000 to 1 million gallon tanks that were filled with true waste. And when you hear about leaking tanks at Hanford, they're mainly the true tanks are leaking, not the high level waste tanks. And there's a couple of leakers, but most of the big leakers are the transuranic tanks. So that's where the waste, high level waste and transuranic come from. Now, what's happened since 1970, and unbeknownst to most people, is that we got rid of most of the cesium and strontium. We removed a bunch of it, and it's been through 1 or 2 decay lives. So now the tanks are transuranic or low level. There's no high level waste left in any of these tanks. There's nothing above 1 curie per liter in any of these high level waste tanks. But we still call them high level waste. And we're still treating them as though they're high level waste. Now, when many of us have been trying to convince, and DOE included, because DOE understands this, why are you treating this waste, which is now transuranic or low level, as high level waste? And you ask the state, you ask the public, and they pretty much, they're just afraid. They're just afraid of radiation. And they think, oh, well, we have to do it because it was high level waste. It's like, no, reality counts. You need to treat it based on what it is, not what it was. So again, this whole idea of radiation and fear, now we are doing very foolish things with this. We're treating it like it's high level waste, and it's not high level waste. And there's 57 million gallons of this. Now there's some at Savannah River and elsewhere, but Hanford has the major tank waste in this country. So we're treating 57 million gallons of transuranic and low level waste as though it's high level waste, simply because of fear of radiation. So Hanford, the regulatory framework, as I mentioned, 4 millirem per year is the limit for most radioactivity associated with DOE and other radioactive materials. So if you go to the closest body of water, which is the Columbia River, at the river's edge, throughout time, for the next 100,000 to 1 million years, the dose coming from Hanford, from these tanks, leaking tanks, cannot exceed 4 millirem per year. Now, I mentioned the background here is about 400. So, I hate to throw this up. This is from the Hanford Tank Waste Environmental, the EIS, the Environmental Impact Statement. Now, no one ever reads these. This one is about 1,200 pages long. It's kind of boring, but it's very interesting because it shows you, okay, let me back up. This is a little complicated here. So we have tank closure alternatives. Either you turn it into glass and you ship it to Yucca Mountain, or you do something else with it. By law, right now, we are only allowed to vitrify this. And so all of these are the same, except you put a Record cap or you backfill with grout or whatever. But you're basically taking the waste out of the tank, vitrifying it into glass, and shipping it somewhere else. Now, with any EIS, you have to have a no action scenario, meaning you just walk away from the site. You don't do anything. You just walk away. And so this is the inner core boundary in the 200 area. This is the Columbia River near shore. This is what's really driving this. So right now, if you walk away from this site, you don't do anything to these tanks. The peak dose in the year 4978, I love the significant digits here, 4978 is 4.37 millirem per year. Now I mentioned that the limit was 4. Okay, so this is just barely over the limit where you have to do something. And if anyone trusts modeling out to the year 4900 in 3 significant digits, you really should question yourself. That's about 4. So let's say that's about 4. Okay, so that's the limit. And that's if you do nothing. Now, all of these, when you take the waste out of the tanks and you vitrify it and ship it to Yucca Mountain, all of them drop to 1. I mean, this is about 1. Again, the number of significant digits here is very funny. So you're dropping all this, you know, we're talking about, including Yucca Mountain, we're talking about $500 or $600 billion. To drop the dose at the river's edge from 4 millirem to 1. Now, the reason this is 1 is this is essentially controlled by what has already leaked out of these tanks. So there's no getting that back. Okay, so so that's that. So I'm not sure if everyone gets that. If you do nothing, you're at 4 millirem a year in a background dose of 400 millirem a year. And if you spend $300 or $400 billion, you can get it down to 1. Now, showing the impact of that, this is 4 millirem per year compared to other normal background doses. Again, annual exposure from natural radiation across the United States is about 300, although it varies, higher than that in many areas. So let's look at 4 rem. Well, it's about twice the amount you get going from coast to coast on an airplane. Okay, well, that's something. Oops. Okay, so it's about here. It's about in here. Now, if you just grout these tanks in place, you don't even take them out, put them something, you just grout them in place. And again, DOE is not allowed to do this officially. That's okay. This is a non-DOE estimate. Again, you know, and it's about 1/10 of the price. You drop it to exactly what you get if you vitrify it or remove it and send it someplace else. Again, because you're solidifying it and you're preventing it from leaking over a short term. And that's all that counts. So at the river's edge, just grouting in place. So it doesn't really matter what you do with it, as long as you do something with it to solidify it and not have it remain as gunky, wet peanut butter, you're doing the best you can. So in terms of levels, if you have to get down to 4, or there are other limits at about 15, if you're down here having to clean up DOE sites to this level in a background dose that is 100 times that, and you just raise that to say 100 millirem, now that's much lower than background, you would save about $420 billion to DOE. And you might say, well, that's not that much, but it actually is, because the taxpayers of America, pretty rough right now with COVID and unemployment, and we're entering a deep recession, if not a depression. Coming up with $400 billion extra dollars just to, not really for any benefit, is a rather large lift. And at some point, you know, taxpayers are going to say, we're not going to do this. So again, DOE is caught between a rock and a hard place. They understand what should be done, and they also understand what they're being required to do. And most of this is driven by fear of low levels of radiation, because these are low levels of radiation. Okay, so the Hanford tanks, vitrification shipment to Yucca Mountains costs about an extra $200 billion, and it'll save 3 millirem a year in the year 4900. relative to either reclassification, shipping to WIP, or something else. So for all other decommissioning and cleanup activities at DOE sites, raising the limits to something reasonable would save another 100 billion. And globally, the cost for compliance to this linear no threshold dose standard is upwards to $1 trillion. Now, again, this is all about risk, and risk is really best discussed relative to other risks. I mean, risk does not stand in a vacuum. So let's look at the risks, the mortality rate of different energy sources. This is deaths per trillion kilowatt hours produced. And of course, coal is the worst. Coal, if you need an evil, coal is evil. And it kills about 100,000 people per trillion kilowatt hours produced. So China's been pretty bad. They're cleaning up their act a little bit. About 7 years ago, this number was 250,000. The United States is pretty good. We only kill 10,000 per trillion kilowatt hours, which is about 15,000 total in the United States. Oil is better, it's not that great. Natural gas is better, not that great. Biomass, everyone says biomass is so great, but the World Health Organization is just declared that biomass is an epidemic in the third world countries because of poor ventilation. Now solar, everything down here are accidents. So, you know, falling off of roofs, falling off of solar arrays, falling off of wind turbines. Hydro, no, this is dam failure. It's not so good. United States, actually pretty good. Nuclear, this is with Chernobyl, and I threw in a few hundred deaths from Fukushima, although that will never happen, just to be nice. And nuclear in the US, you know, this is one guy that fell off a scaffolding, broke his neck. So these are all accidents, and they're preventable. I mean, the nuclear industry in the United States is great, very safe. I wish everything else was as safe. But for coal, hydro, and nuclear, I have a global average, and then I have a US. Now, you know, why does coal kill fewer people in the United States than elsewhere? And of course, I can't see a show of hands there. But if anyone wants to shout out, why do you think coal kills fewer people than the US?
Less factories.
Good guess.
Higher safety standards.
Yes. The Clean Air Act. The Clean Air Act, I think it was of 68, can't remember now. The Clean Air Act has arguably has saved more lives than any single piece of legislation in history. And that's why this is the case, the Clean Air Act. So when anyone talks about rolling back the Clean Air Act, I want to kill them. Oops, sorry, that's probably not good. Hydro, why is this so much less in the United States? Shout it out.
Higher construction and reliability safety standards in the United States?
Actually, you might think that, and it turns out, no, it's FERC, the Federal Energy Regulatory Commission. They actually inspect dams. And if you have a crack in your cement, it might have started out as great, you know, high quality cement. If you have a crack in your cement, they will shut you down. They just did up here, actually. We have the big hydro dams up here along the Columbia. And they shut down Priest Rapids, because this huge dam, because they found a crack in the cement and they had to fix it. And that's great. So again, these 5 people are people that just fell off heights and broke their necks, kind of thing. However, in the world, a lot of places don't inspect the cement, and sometimes the dam fails and it wipes out, you know, whole villages. So it's really bad when it happens. It doesn't happen in the US hardly ever. And that's why. Now, what about nuclear? Why is nuclear so much safer? Nuclear Regulatory Commission, NRC. I know the public tends to think NRC is a bunch of shills for the industry, but the industry does not like NRC. They shut them down for very minor things. I mean, you have to really pass inspection for NRC. So yeah, so we never have a problem. And that's great. I love it. In fact, recently at the nuclear power plant near me here, they instituted, you cannot walk up and down stairs without one hand holding onto the railing. Now that seems reasonable, But if they see you, you will be fired on the spot. You'll just be fired. Now that doesn't happen in office buildings. Okay, so totally, everything's proceduralized. Everything is safety conscious more than anything else, and that's why the nuclear industry is so safe in the United States, because everyone's always thinking about safety. Now here's Beijing, which Beijing, not China, but Beijing itself is about 80% coal. And this is what it's like. And it's not very nice, not very healthy, really bad. And in the case, they've been putting up big screen TVs because they know how depressing it is not to see the sky for long periods of time. This is not how I would have handled this, but it's very interesting. Now usually I would shout this out. So I want everyone to shout out. What's the most dangerous thing on this list? Shout it out.
Driving?
That's top 4.
Alcohol?
Top 4.
Opioid.
Smoking tobacco.
Okay.
That's the top 4.
Iatrogenic.
Aha! You and I know that because we're over 60. Okay. So, all right. Iatrogenic. Smoking actually is the worst, always has been, always will be. The lungs do not like breathing in burnt particulates. That's just the way it is. Now, iatrogenic is medicine gone wrong. It's not malpractice. It's not abuse of drugs. That's the opioid deaths, which is a new line I put on there recently, which is horrible. It's simply don't know why the patient died. Heath Ledger was an iatrogenic death. I hate it that he died, but everyone knows the name. Even Michael Jackson was an iatrogenic death, although it was ruled a homicide, but it was really iatrogenic. Prince was an iatrogenic death. So anyway, just, properly prescribed, properly taken, proper surgical procedures, just don't know why the patient died. And it's been growing dramatically in the last 10 years as the population ages. Now, food poisoning, why are we killing this many people with hamburgers? I don't get it. And of course, nuclear one. This one guy 3 years ago fell off scaffolding, broke his neck. Now, a biostatistician gave me grief recently because I hadn't normalized to the subpopulation. Here it is. This changes it. Now, iatrogenic drops to number 3. In police work, I mean, not that many people die, but there's not that many police officers. So it is actually relative. This is not a true risk factor. It's a relative danger index. And it's nice to know that eating is only slightly more dangerous than nuclear power. It's supposed to get a laugh too.
800 times more dangerous.
Yeah, a lot more dangerous. It's so bizarre. You wouldn't know this from the public, but the nuclear industry is the safest industry in human history. The nuclear industry is the safest endeavor that humans have ever engaged in. And you should think about that because it's really, really important. And nuclear waste itself is, no one's ever died from handling nuclear waste. It's easy to handle nuclear waste, easy to shield, easy to transport. And yet, people freak out about it so much. It's just incredible. And that's ignorance, but it's also the effect of this LNT, the linear no threshold dose, that was adopted in 1959 as the global regulatory limit. And it has been horrible. It was a very political decision at the time, actually. Nothing to do with science, as usual. But we have been paying for it. Thank you.
Okay, so I'm sure Jim would be happy to address any questions that you may have. Fire away.
I have one. Can I start, Peter
Yes.
Stevens? When you were talking about the estimates of radiation near shore on the Columbia River, 4.37 millirem per year in year 5,000, essentially. But there have to be error estimates on that. In other words, it seems to me that the likelihood that that number is wrong is greater than the risk of whatever accident you might be thinking.
Absolutely. Now, and this again, this came from the EIS, the Environmental Impact Statement, and they didn't put any error bars on anything because you have no idea what the error bars are. I mean, they're really plus or minus 100%. I mean, it could be anything in there.
Yeah, I think it's plus a great deal more than 100%.
Actually, no, I think it's much less. But again, when you pick the properties of this material and you put them in your modeling, and that's what I did in the 90s essentially to come up with those that DOE uses in those numbers. When you take the range in hydraulic conductivity and diffusion coefficient and retardation factor, all the chemical interactions that are going along the path, we generally pick them very conservatively, and so it's probably much less than that. But again, yeah, the idea that you have three significant figures is a joke. It's, you might say 4 plus or minus 4, or maybe plus 10 minus 2. I mean, whatever. It doesn't really mean that much, except that it's probably very low. And in fact, it's right up bumping up against the limits, the regulatory limits of having to do anything. And so you might suspiciously say that 4.37 is just over 4 for a good reason, because if it were under 4, you wouldn't have to do anything. And of course, the public would scream bloody murder. So again, you have to do something. What you're going to do doesn't really matter as long as you stabilize the waste and make sure has no free liquid in it. And if that happens, then you pretty much drop to essentially zero. It takes so long for everything to go along that path, and the path sticks, everything sticks to it so well that that almost nothing gets out except maybe technetium and neptunial and a few things like that, which aren't in very large concentrations. So by the time you get 10 miles to the river in the subsurface, your concentrations are so low. And that's right at the river's edge. That's coming out of the soil. Once it gets into the river, it's not even measurable because the flow of the river is so huge. So, again, you pick the situation you want to drive the actions, right? So you say, well, it's over 4, so we have to do something. And it's right on the river's edge, so we have to do something. And the law, Yucca Mountain's the law of the land, says you have to vitrify it and send it to Yucca Mountain. Now that will never happen. And you should get me back to talk about nuclear waste disposal. But it'll never happen because it just costs too much. The Nuclear Waste Fund will never be able to handle these numbers. And we'll never have enough extra money to spend $400 billion extra doing something stupid. So most of it will stay right where it is. Most nuclear waste in the country will stay right where it is. If we're smart, it'll all go to WIP or to another salt repository near WIP, whatever you want to call it, because that's the best rock for this problem. But that's a whole nother talk.
Jim, I have a question on the disposal. You're probably aware that back in the 1970s and I think 1980s, there was a program to explore what was called subseabed disposal. It was operated by the Sandia National Lab.
I know it well.
Okay.
I know it well.
Okay.
Brilliant, actually brilliant.
It was, I thought so. And it died a political death, but technologically it seemed that it was the cheapest, safest option for disposal of high level waste.
Oh yeah, we had penetrometers from the Vietnam War era that would be put on packages and go into the goo and get them down, penetrate them to about 1,000 feet in this cold, organic, I'm sorry, not organic, this cold reducing muck. And there was no geologic mechanism to get them back out. I mean, there's no way they can get back out. Right. And you didn't have to be perfect. You just had to be over a huge trench and just drop it in. I mean, it's not like you had to pinpoint it.
So do you think that ever is going to get revived as an option in the US if Yucca Mountain has too many lawsuits involved?
Never, because you bump up against international law. You can't transport radioactive materials across the ocean into global waters, international waters like that without agreements in place. And I mean, of course, we could ignore the agreements. We seem to be doing that now, but yeah, unlikely. Also, you know, the salt is perfect. I mean, the Permian salt, as a geologist,
Yeah.
it takes water 1 billion years to move an inch in the Salado salt formation that WIP is in. That's what you
Right.
want. You don't need engineered barriers. You don't need anything. You don't need super copper canisters. You don't need to vitrify. You just need to meet Department of Transportation requirements to get it there. And then you're in the salt, and the salt seals itself. It creeps closed over time. It's brilliant. And I worked on that for 10 years. I worked on Yucca Mountain for 25 years.
Yeah.
And, you know, there's no question that Yucca Mountain is a stupid place to put anything, and WIP is a brilliant place to put something.
Can I ask a question?
Yes.
So in your early studies, plots of the risk versus various kinds of cancer deaths versus
Right.
dose, you just had a plot for solid cancers. I mean, I have a feeling lymphoma or blood cancers don't count as solid cancer.
Right. I mean, there are different studies that had different types of cancers, because it's hard to compare apples to apples, and so you want to, you know, do that kind of thing. All was doing is that as a and they had those kind of studies for everything, leukemia, everything else. All you're seeing is that the effects disappear at about 10 rem. There's nothing below there that is statistically significant. But above that, it is quite linear.
You would have gotten the same plots if you plotted other kinds of cancers.
Right.
Okay, thank you.
Could I ask a question?
Yes.
By the way, Homer Simpson, you're being a little unfair to them. I mean, because after all, he drops a piece of solid waste in the beginning of every show.
That's funny. Yep.
But I guess my question is, isn't the reason why people are afraid of nuclear weapons and waste and so on is not because of the averages? And maybe that education is,
right.
We're pretty lousy at educating people. It's because we believe in accidents. And that's why there's a fear up the Hudson River. That's why there was a fear in Long Island. And that is, and we are afraid of asteroids hitting us.
Right.
So Chernobyl was a really bad day for nuclear energy. It's a visible thing that people see. And I think that maybe that type of education of this issue of averages versus catastrophic events is really what gets in the way of the public's acceptance of anything you said.
Right. And in fact, and that's true. And education is so difficult. I mean, really, really difficult to get everyone educated. But more than that, politics took its toll. Ellen, you know, the whole purpose of the Cold War was to scare everyone about nuclear, and it worked really well. It just kind of lost the subtle differences between power and weapons, but it was purposefully done. In fact, LNT was adopted and used by Russia and China to stop American above ground nuclear tests. That's really what did it. Okay. That's a purely political thing, had nothing to do with science. And so, but the whole purpose of Cold War was to scare everyone about nuclear, and it worked. And so it's hard to reverse that. I mean, I just saw a commercial on TV about car insurance, and it mentioned a nuclear bomb. I mean, come on. I mean, what does that have to? It's just so in the culture, so deep, that I'm not sure it can actually be gotten rid of. And I thought, you know, fear of climate change would certainly reverse that. But, you know, Jim Hansen's been beating his head against the wall for years now, and he's quite disgusted because people that say they care about climate change are actually more afraid of low levels of radiation than of climate change, which is insane.
I think a lot of the fear of radioactivity, I think Jeff asked a very important question. I think partly as well, I don't know about you, but I grew up watching science fiction movies where some innocent creature walks through a radioactive cloud and turns into this heinous monster that eats babies and tramples on innocent people all around the world. And I sort of, you know, I was 10 and 12 years old when I was watching those movies, but it had a lasting impact on me, and probably on a lot
Yeah.
of people, that there was, people are afraid of radioactivity, but most people don't know what it is. So it's partly
Right.
the fear of the unknown, and you know that an innocent creature can turn into a monster if it if it's exposed to radioactivity. And so I think there's a lot of our fear is related to those things that we were cultural things that we were exposed to back in the day.
Yeah, Marvel Comics wouldn't have been anywhere without radioactivity.
Yeah, right.
But one of the problems there is science fiction, because it's like Fallout is such a big deal in science fiction and such a big deal in terms of fear of radiation. There was no fallout, or no significant fallout, from Hiroshima and Nagasaki. People think there was. There was no fallout. And there's no fallout if you detonate your weapon at the correct height above the ground to maximize the yield, which we actually did then. The only time we ever get fallout is when you make a mistake and you detonate your weapon too close to the ground, and you drag up stuff and it gets activated, and you bond a bunch of stuff to it, and then it falls out. But there was very little fallout. We did about 1,000 above ground nuclear tests in America, and there was 3 or 4 of them that actually had significant fallout, and those were mistakes because we underestimated the yield of those weapons. So again, I mean, 2 months after Hiroshima and Nagasaki, the background levels of radiation were back to normal, and so there's no dead zone. People are going to have dead zones for 50,000 years. It's like, no, you won't. You don't have dead zones. So it's a combination of decay. It's a combination of geologic gardening. Soil kind of tends to garden, turbation, things like that. You don't build up dead zones from fallout from nuclear weapons, and you certainly don't do it from nuclear accidents from reactors. So yeah. But those are pretty complicated concepts to get across to the public.
There is a current, being a devotee of left-wing alarmist radio, there is a one interesting accident that has been talked about a lot, and that is plutonium-driven engines propelled into space. And crashing back to Earth, and what the effect would be. So I think this issue of catastrophe is really what drives a lot of the sense of danger in the human population, right, about radioactivity, more than I think any other danger we can think of.
Yep. And the bizarre thing is that there's so little radioactive materials. I mean, the amount of, it takes 11 million times less nuclear fuel than coal to make the same amount of material. I'm sorry, to make the same energy. And so the amount of nuclear materials, the amount of nuclear waste is so trivial compared to almost anything else in our society that, it's like you just can't get a lot of it. It's really hard to get a big dose. That's why no one ever dies from radiation. Really hard to get a dose. And so, spaceships, falling back with, plutonium, there's just so little of it in there that it gets dispersed and you never see it. But it makes a great story.
Okay, who else, any other questions?
Yeah, I've got another one, if I may. I've heard for the first time about low-level radiation being therapeutic for cytokine storm. Can you point me to a reference on that, or?
Yes, Nicholas is going to send that around.
I just received it, and I'll be happy to distribute it.
There's a good technical paper that he's going to send, and then I posted on it in Forbes a couple of times, so he'll give you that link. Okay. But that particular paper by Jim Welsh and company is brilliant. And it doesn't treat the virus. It doesn't kill the virus.
Understand.
What it does, when in viral pneumonias especially, kind of can make your immune system go wacko. And the immune system is really complex. I mean, there's T cells, there's killer cells, there's lymphocytes, there's macrophages, there's all sorts of cells that respond to certain things, and they interact with each other. And especially the macrophages, they can either cause inflammation or decrease inflammation, and they work together with other cells to decide what's needed. Okay, now sometimes inflammation is great. Okay, sometimes, but when it gets out of hand, it's bad. So all COVID does in a certain number of cases is it causes this cytokine. The cytokines are just little protein fragments that cause the immune cells to behave certain ways. All it does is get really wacko, and the macrophages start promoting inflammation to an incredible degree. And a low-level dose of radiation, about a half a grade to both lungs, pretty trivial, about 100 times less than what we use in cancer, to both lungs will pretty much, it repolarizes the macrophages from pro-inflammatory to anti-inflammatory. That's all it does. It's very neat. And then it goes about its business, and your body then has time, instead of dying from pneumonia, it has time to fight it off on its own.
So if I get a serious long-term reaction to COVID, which I hope I don't, where can I go to get therapy for this?
You go any hospital, any cancer treatment center. We're already set up. No new training, no new procedures, nothing. You say, you go down to radiology, I want a half a grade of both lungs. Now they might, say, wait a second, and usually, no, I insist, I don't care. And you don't, it's not like it's not a diagnostic, okay? So you don't want someone interpreting some images or anything, which is what costs so much.
Right.
In general, you simply want a half a grade blast to your lungs, period.
Okay, and there are radiologists who will do that for me?
I'm not sure. I've been trying to get this out. In fact, a group of radiation oncologists and myself have been trying to get this out. And it's amazing, the pushback, because again, L&T rules, even the medical industry. And so, doctors who don't know much about this will say, oh no, the radiation is dangerous. There's too much side effects. It's like, what are you talking? There's no side effects to that level. We've never had any side effects to that level. So again, this is a very difficult thing in our society. Very, very difficult.
That's interesting.
However,
I read the Forbes article that you wrote.
Oh, good.
But I didn't see a reference to something that I can sink my teeth in.
Right. There was a link in there, but I just have links all over the place. Yeah. So Nick will send out that paper. Very good paper. Very understandable, even if you're not an epidemiologist. But again, it's the cytokine storm. So you need to do it at the right point. If you have to go on oxygen, you're in a cytokine storm. If you have to go on a ventilator, you're in a cytokine storm. So that's when to do it. Now, if you're on a ventilator, you may have sustained a lot of damage anyway. But if done at the right time, it's 90% effective.
Yeah, amazing.
That's rather large. Okay.
Yeah.
Are there human trials going on now at different hospitals to assess?
Yes, they're trying. Again, getting human trials is a long thing. There's been some small ones with 10 people or so, but the biggest databases in history. We used to do this in the 20th century, and then we stopped when the fear of radiation became big. But even Oppenheimer used to do this for viral pneumonia, and it was 80% effective then, and we're better at this now. So again, there's plenty of data on this, and it's not like a new drug. You're not looking for some weird side effect you've never seen before. We've been doing this for 75 years.
Fascinating.
That's really interesting. Yeah. Okay.
Thank you.
Oh, Professor Nicholas?
Yeah,
I'm
please.
sorry. I actually have a question for Jim. So, little background. I have dual citizenship to France, so my family talks about, I guess, everything that's going on there. And they told me that their country is mostly run off of nuclear power. So I was just wondering why they were able to expand their resources versus us when, we're usually more competitive when it comes to things.
Well, that was because of the oil embargo in 1973. I'm not sure if you remember that. I remember it well. Gas prices went from 32 cents a gallon to a couple of bucks, and I was, had just started driving a lot, so it was kind of strange. But 1973, oil embargo. France said, forget this. We're not going to kill ourselves on fossil fuel. So they decided to go mostly nuclear, and they built all of their reactors, which is I think about 57 or so, in almost a 10-year time period. It was really brilliant. Now, right now, though, if you look at polling in France about nuclear energy, it's dropping. People want to get rid of it, which is insane because, France has the best air quality in Europe because they don't have any fossil fuel. So now the French government is saying right now they're about 80% nuclear. And in fact, they produce almost 100% of what they need. They just sell some of it to Germany, of course, which is ironic. But the French government is now angling towards getting it down to 50%. Now, if they're going to lower that to 50%, what's going to take its place? Well, it's going to be natural gas. Wind and solar do not replace nuclear. Natural gas does. It's cheap. It's easy to build natural gas plants. Doesn't take any material at all. It takes a fraction of the steel and concrete that everything else takes. So it'll be natural gas, and that's too bad. I mean, it's really sad. But yeah, France told us how to do it. And also the reason it was so successful is they made them all the same. The problem with the United States is we made them all different. We were experimenting, right? So, and of course, classic capitalism. So competition. So everyone had their design out there and everyone was different. And it's like, well, that's not the way to bring costs down or to make everyone feel good about it, is by having everyone different. So that's the problem. We need to get to the SMRs, the small modular reactors. They're brilliant. The one over here in Oregon has pretty much been approved. It's brilliant. Can't melt down. All the scary stuff is fixed. We haven't been idle in the last 30 years. But again, the fear of radiation is preventing it from really doing anything. And my fear is that, we're going to be 60% fossil fuel in 2050 because we're not doing the right things.
Thank you.
Okay, any other?
Students, give me questions.
There you go.
You keep trying to get students to speak up. I have to leave, but I want to say thank you very much.
You're welcome. This is fun. Good audience.
There's a question in the chat.
Okay.
Oh, good.
Let's see. The question reads, do you think death rates are so low with nuclear energy because we haven't embraced it as a primary energy source as much as we have with coal and fossil fuels? Do you expect mortality rates to increase if we transition to nuclear energy as a primary energy source? That's the question.
No, I actually, these numbers are, let me share the screen again here. These numbers are normalized, right? Come on, share. These numbers are normalized, all right? 2 trillion per trillion kilowatt hours. Now, nuclear is not a minor player. It produces 20% of our energy. That's actually large. Coal only produces 30% and gas about 35%. So nuclear is pretty big in this country in terms of amount of power. And that won't change because it's all procedural driven. It's all safety driven. So even non-lethal accidents in the nuclear industry, it's safer to work in a nuclear power plant than it is to sit at a desk trading stocks. Now that does not seem, now that's OSHA data, and that doesn't seem reasonable, except that everyone is just safety conscious. So out at Hanford, I had to take ladder training. I had to take training to learn to use a ladder. All right, now that's kind of funny. I didn't know that much about ladders. It's quite an interesting course, but that's kind of insane. So, and you can't operate a ladder without 2 qualified operators of a ladder. Do you think anyone ever falls off a ladder at a nuclear power plant? No, Never, never. But you know, at the 7th story of the AIG building in New York, someone's standing on a rolling chair hanging a picture. I mean, you know that, right? So they fall off, they break their arm, gets reported to OSHA. That's what this is. So it's just that everything in the nuclear industry is rapidly proceduralized, right? You have to follow procedure, and that's why procedures are written, because you don't get hurt if you follow procedure. You always get hurt if you don't follow procedure. So that's it. So I wish, the wind and solar, I have solar panels on my roof, and, I couldn't believe these guys walking around the parts of my roof. It was so dangerous. They were not roped up. I mean, it was a 40-foot drop on one side, and I would never go on that part of the roof. They were just wandering around like it was nothing. And occasionally they fall off, break their neck, and that's what this number is, this 440 in solar, just people being careless. So all of these numbers could come down to as good as nuclear if they were careful. And hopefully they will become careful, right? I can't believe you'd actually climb a wind turbine without being roped up. That doesn't make any sense, but people do.
Jim, there's another question posed on the chat here. It says, were there any nuclear power plant incidents caused by budget cuts, such as long working hour shifts, difficulty procuring replacement parts, or not being able to afford critical maintenance?
No, because those, again, they're determined. NRC will shut you down if you don't follow your maintenance schedule and things like that. The only thing that happens occasionally is if you have really bad weather, like occurred here during the fires, really hot weather or really cold weather, the local energy operators, the ITOs and things like that, they will ask the nuclear power plants to delay maintenance and keep running because they need that energy, because the wind turbines aren't turning, or the solar panels are not producing, or natural gas is being, you can't get enough of it through the pipelines. So they'll ask nuclear to delay maintenance for months. And they do that all the time. It doesn't cause any real problems, but it just shows you that nuclear energy is just so dependable that the energy controllers want that energy to be able to use in times of bad weather.
Thank you. So we have time for one more question. Anybody?
I have a question.
Good.
So to be as sustainable as possible, like a perfect world, would that include, do you think that would include having mostly nuclear power, maybe along with hydro or wind or solar?
Yes, Nick has to get me back to talk about this, but there is a Green New Deal that works. Let's see what it is. No, let's see what it is. Here it is. In America, this low carbon, call it Green New Deal, whatever you want to do, but 500,000 new megawatts of wind turbines, 200,000 megawatts of new nuclear, 300,000 megawatts of new solar, and 120,000 megawatts of new hydro, including existing hydro. That will do it. That's hard. It's hard to get to, mainly because people don't realize the material requirements for renewable. So again, this is concrete volume, volume of concrete and mass of steel required to produce a megawatt of energy from these sources. And again, you see, wind requires 10 times more steel and concrete per megawatt. Solar requires much more steel, but not much concrete. Hydro requires a ton of concrete, but not much steel. And these require not very much at all. Now, this is why gas is so good. You could just throw up a gas plant in a year. It takes nothing. It takes no steel, takes no concrete. It's just, you can just throw it up. And that's why state legislatures love them. And also gas is cheap, and we have lots and lots of gas. So this is what's driving it, not anything else, unfortunately. And that's why when you shut down nuclear, you replace it with gas. And that's sad. So if you're going to produce this much, let me put this up here. What's the fastest growing energy sources in the world? Amanda, shout it out.
Sorry, I'm eating. Is it the fastest growing energy source in the world? It is natural gas, isn't it?
It's oil.
It's oil.
Bummer.
Okay.
Look at that. Oil, coal, and natural gas. This is not good. This is not what we want. Okay. And so we have these three, and yeah, renewables are coming up, but people talk about getting rid of hydro or getting rid of nuclear. It's like, well, they're the only ones that have done anything against fossil fuel. If you get rid of those, then your renewables are going to spend all their time replacing those and not replacing fossil fuel. You need all of these. You cannot do it without all of them. And so when we talk about, what we need to do, we need to get rid of these and we need to bring up all of these, all of them. You can't be, you can't be, oh God, what's the word I want? Anyway, you have to be ambitious, okay?
Yeah, you can't rely on just one.
Yeah, you can't. I mean, we can't build enough of one. And also one is not perfect because, and if you build wind turbines, okay, you build wind turbines, you have to build them in Tornado Alley. Anywhere where it's green, to put a wind turbine is a waste of steel. You don't produce enough energy, okay? That's insane. So you produce, and that's why a lot of wind turbines are in Tornado Alley, like, huge, Texas, Iowa, everyone's putting in wind turbines. I mean, even birds realized about 1 million years ago that you don't migrate through Tornado Alley. There's no bird migratory routes down here. They're all out here. So if you care about wind turbines killing birds, you also should put them in Tornado Alley, right? Now, and the same thing with solar. You need to put them in the red and orange. Why would you put them in Maine? You don't, it takes a lot of steel for solar. You're just wasting steel. We don't have enough steel. So again, there's a lot of other things that people are not thinking about when they're just saying, oh yeah, we need more of this. Yeah, well, there's a way to do it and there's a way not to do it. And that's the way to do it. And here's NuScale's new nuclear SMR, small modular reactor design. It's really brilliant, I must say. And even hydro. You can double the amount of hydro in this country without building a single new dam. These are the dams that are not electrified. You can electrify them. That's a lot easier than building new dams. And you've already done the regulatory issues. The public is already okay with them. So again, there's ways to do this and ways not to do this.
Right, thank you.
Thank you.
And I think we have to wrap this up, but Jim, I know I'm speaking for the entire audience. Thank you very much for a very stimulating, provocative talk. I expected nothing less, and we'll look forward to the next occasion. So
Excellent.
thank you very
Thanks so much.
Okay.
Wonderful.
We'll be in touch.
Perfect.
Thank you,
Thanks.
that was awesome.
Thanks so much. Bye.
Bye.
Bye.